Welcome to Mastering Solutions. Let's first make a list of everything that we're given in this problem. We're told that the interference pattern on a screen 1 meter behind, so L is 1 meter, and the diffraction grating is 800 lines per millimeter. So D, or the diffraction spacing, the slit spacing, is width over slits, or width over lines, either way. And then we have 1 times 10 to the negative 3, so 1 millimeter over 800 lines. And I like to leave it like this so it's more precise when we plug it in. And that's all that we're given. We have the figure, of course. And what we have is this interference pattern. This one here in the middle, it's the biggest, and it's the central maximum. Off to the side, equally spaced, we have 2 more bright fringes. And so these are going to be the M equals 1 fringes. And then the next ones will be equal to, of course, M equals 2. Oh, I wrote 2. That's supposed to be a 1. And then M equals 2 over here. So to figure out the wavelength of light, it's a very similar process that we've done on some of the past few questions. We'll use the equations y is equal to L times the tangent of theta, but we have to figure out what theta is, and it's not given. So in a lot of the other problems, we would start off by using sine of theta is equal to m lambda over d. This one, what we're going to do is we're going to use theta is equal to inverse tangent of y over L. And so we have y, because that is the distance from the central max out to a bright fringe. So for M1, that's 43.6. For M2, it's 43.6 plus 89.7. And then L is 1 meter, of course. So let's plug that in for M of 1. So we have y is equal to, well, let's do the degrees first. So we have inverse tangent of y, which we will say is 43.6 times 10 to the negative 2 meters over L of 1 meter. So we can take the inverse tangent of 43.6 times 10 to the negative 2. And so we have 23.55. Oh, and make sure your calculator's in degree mode for this, otherwise you'll get radians. So we have 23, I'll do a longer, 557 since it's an intermediate answer. Okay, so that's the degrees that we have. Now we need to figure out wavelength, but none of these equations have lambda in it. So now is where we're going to use that other one that we talked about just a moment ago, where we have theta is equal to the inverse sine of m times lambda over d. We need to isolate lambda though. So we'll take the sine of both sides, and then, well, let's do that first. We have sine theta equals m lambda over d. Now we'll multiply both sides by d and divide by m. So those cancel, those cancel. So we have, we have d over m times sine of theta is equal to lambda. And you could also rewrite this equation this way. Lambda is equal to d sine theta over m. These two are both saying the same thing. And so let's plug in our values for the wavelength. We'll use m of 1 at first. So we have our d, or the slit spacing, is 1 times 10 to the negative 3 meters over 800 slits. And then we're going to times that by sine of 23.557. All of that is over m, which in this case is 1, of course. So we have 1 times 10 to the negative 3 divided by 800. Then that is multiplied by the sine of 23.557. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 500 nanometers for the wavelength. Okay, so now I just want to give us some more room here. We can double check ourselves by doing the same thing for m of 2. So our equation here is inverse tangent of y over L. And so we have inverse tangent in this case is going to be 43.6 times 10 to the negative 2 meters plus 89.7 times 10 to the negative 2 meters. Because we needed to add this distance plus this distance, go from the central max out to M2 over L, in this case, is 1 meter. So for this one, we have the inverse tangent of 43.6 times 10 to the negative 2. And if you want to just move the decimal place over 2, that's fine as well. Plus 89.7 times 10 to the negative 2. So that gives us 53.123 degrees. So that is our angle for M2. And now we can plug that into here. So we have 1 times 10 to the negative 3 divided by 800. And then we'll multiply that by the sine of our angle, which we said was 53.123. And then let me add a parentheses. Oh, I did already. Okay. So now all of that gets divided by our m, which in this case is 2. So that gives us, look, 500 nanometers. So we know that we did everything right because we double checked ourselves and we got 500 nanometers for the wavelength for both M1 and for M2.